We were discussing how to make the opamp. You need to have some way to calculate the difference and then integrate the difference. Integrating the difference is using a capacitor, and then to find the difference between the two, you use a transconductance, that is a voltage controlled current source with a difference input. Okay. So now whatever difference voltage you have here, maybe we'll just call it VE, then the output will be the integral of that. Okay. So this is the simplest op-amp, and again, if we, and of course, to not be distracted right now with loading, I'll have an ideal buffer. Then you can make an amplifier using this, the negative feedback amplifier. This is the negative terminal of the op-amp, this is the positive terminal, and to which you connect your input voltage. Okay. So this, we will go into the implementation details, but the implementation of this, the basic implementation would be a differential pair with a current mirror load. It has a differential input and a single-ended output. Okay. And of course, we assume it's biased at the correct operating point so that all the transistors are in the saturation region and so on. We know that at the operating point, the incremental equivalent of this is a controlled current source in parallel with some output conductance. Okay. So that means that this can be described by some transconductance and some output resistance. Okay. Now we saw that the effect of the output resistance is to cause a steady state error with DC inputs, right? That is to support a non-zero output voltage, you have to have some current flowing out of the transconductor, and to have a current flowing out of the transconductor, you have to have a difference voltage at the input. Okay. So now, of course, ideally we wanted the difference voltage to settle to zero. It's not going to do that. It will settle to some non-zero value, and that's the steady state error. Now, the larger the DC gain of the op-amp, that is, the DC gain of the op-amp is GM1 R01, the smaller the steady state error. Okay. This VE is nothing but the virtual short voltage. Ideally, it should be zero because of infinite loop gain in negative feedback, but in reality it won't be zero. Okay. So this type of op-amp, ideally we wanted to have a transfer function of this type, and in the real case we have where P1 is omega u by a naught, and another way of writing it is you get the extra term 1 by a naught in the denominator. Okay. So now how do we fix this? There are different ways. Again, the transistor level implementation we will postpone for later. Okay. So because in this particular case, A naught is GM1 by GDS1 plus GDS3. This is of the order of intrinsic gain of a single transistor. Okay. So that means that the DC gain you get from this is necessarily limited to a few tenths at most. Okay. You're not going to get a very high gain. It depends on the length, but again, it's not reasonable to increase the gain by orders of magnitude simply by increasing the length, because then the area would just blow up. Okay. So you have to find other ways of improving the op-amp's performance, that is to have a higher DC gain so that you have a smaller steady state error. Okay. Any questions about this? And this type of op-amp essentially whose gain resembles the gain of a single transistor, that is you have a single amplifying stage to speak of, that's called a single stage op-amp. They are used. Now of course, the use could be limited because first of all they cannot directly drive resistive loads, but there are many cases in which the load is capacitive and they can be used. Okay, if you have a resistive load, then the DC gain will reduce even further, that is resistor connected directly to this point. But if you have a capacitive load, that is okay. So this is what is known as a single stage op-amp. Okay. There are variants of this, even improved variants, which we'll see. The improvements can be along various dimensions. As you know, this type of, if you have just a differential pair with a current mirror load, the output swing is limited and so on. So that may be to improve that, it may be to improve the DC gain and so on. Okay. Yes. No. So that is, it depends on the context. Maybe there is a load that you have to drive. And if there is nothing, it is basically the parasitic capacitance of the transconductor itself and whatever else is following it. So it depends on where it is being used. So in some cases, you may have to drive a capacitive load explicitly. But anyway, whatever load means, whatever comes next. So when we come to stability, we'll see. I mean, in some cases, you may have to use an external, extra capacitance to make sure that the poles and zeros are in the right places. So we need to one set of improvement is basically still use the single stage op-amp, but with transistors replaced by cascode combinations. What is a cascode combination? This is a common source amplifier, okay, and the gain magnitude is of the order of GM RDS. Now, if you use a combination of common source amplifier and a common gate amplifier, okay, this incremental is grounded, right? I'm not showing biasing details and so on. What is the difference between these two? This is what is called a cascode. Have you seen this? Everybody has seen this, right? So what does it do? What benefits does this buy you? So effectively, first of all, the current here is GMVI, and that will be the same in this case. GMVI and the output current will still be the same. Only thing is, looking from here, you have RDS as the output resistance, and looking from here, you know the exact expression, but it will be of the order of, if this is called MC, it will be GMC, RDSC, and RDS, where the lower one, or if I call this M1, it's RDS1, this is RDS1, okay. So now the gain, this is of the order of GM square, RDS square, okay. So this can be done. So now every transistor has to be replaced by this. So that is the two transistors of the differential pair as well as the current mirror load. Okay, the current mirror load, it's just being used as a current mirror, but that also has to have, as you see, the output conductance is a sum of the conductance offered by this plus that one. Okay, so you can't reduce only one and let the other be, then that will limit the gain. So you have to increase or reduce the output conductance of both parts. So that means you have to use this cascode combination for both the differential pair and the current mirror. We'll come to the transistor level details later, but basically you have to use it for both of them. Okay. Now, what would be the disadvantage of this? Any disadvantage that you see? Huh? Right. Basically, earlier the output operating point had to be such that one transistor is in the saturation region. Okay. So you have to maintain the minimum voltage required is VD sat of one transistor. So now you have two transistors. Okay. Still, I mean, the VDS could be smaller and maybe this will be better, but you can see there is some compromise in the swing limit. Okay. So of course you can keep going. Now in earlier days when you had high supply voltages, it would be okay, but you can have what is known as a triple cascode. Right. So here looking into this you would get RDS1, looking into this you would get GMC, RDSC, RDS1, and looking into this you would get GMC2, RDSC2 times whatever you have there. Okay. So the overall gain would be the cube of a single transistor's gain. Of course, this is not practical with when you have supplies of 1 volt and so on. When you have a 5 volt supply, perhaps this can be done. Okay. So, or at least like 2.5 volts and things like that, because now you have to have the output operating point should be such that 3 transistors have to remain in the saturation region. So the minimum voltage that you can have at the output, minimum operating point voltage will be VD sat 1 plus VD sat 2 plus VD sat 3. So it again further reduces the swing. Okay. So this is one way of doing it. You have not fundamentally changed anything. Instead of each transistor, you will use these combinations. Of course, they do bring in some complications. You have additional nodes. So that means you have additional parasitic poles and so on. Okay. So that all these nodes will have parasitic capacitances. So that means you have many more poles, and then you have to make sure that your stability margins are satisfied with all these extra poles. Okay. So those things are there, but it is possible to improve the DC gain without fundamentally changing much. Okay. You still use the same structure, that is differential pair with a current mirror load. Okay. So we will see the transistor level details of this. And one sort of assumption I've made here is that I've used an NMOS common source amplifier with a NMOS common gate amplifier. That is not necessary. You could use an NMOS common source amplifier with a PMOS common gate amplifier. We'll see. I mean, when we come to the transistor level details, what the implications of that are. Okay. That is, it turns out that it will give you an advantage in swing, but a disadvantage in noise and so on. Okay. Now, what else do you think this will, okay, one is swing limit, it has been compromised. What else could be a problem? Now, we have additional components. Would noise be a problem? Yes or no? Huh? So, this I think you must have solved in one of the previous assignments. You have seen that the common gate devices, its noise doesn't contribute to the output significantly. Okay. So, noise wise, actually, it's not different from what you had earlier. We will see those details. Okay. So, typically, the advantage is gain and the disadvantage is swing limit. Okay. So, this is one set of improvements. This will give you like one set of op amps. Okay. So, it's very important to understand the underlying principles, because I can start drawing op amp topologies and quickly the number will blow up. Okay. And of course, for every circuit like this, you have the inverted counterpart where NMOS is replaced by PMOS and PMOS is replaced by NMOS. So it can look like you have a lot of different circuits, but if you know how the, I mean, if you know the principles behind the circuits, you should be able to recognize them in whichever form they are. Okay. Any questions about this? So in this case, nothing happens. I mean, you can assume that simply A naught has increased. Like I said, there are some details, that is, you will have extra poles that will come to later. But if A naught increases, of course, the DC steady state error reduces. Okay. Now, what else is a possibility? So now, how do we get integration? You pass current through a capacitor, okay, and the voltage across the capacitor is, okay, or in the Laplace domain, it is that, right? And we have a difference voltage VE, which we pass through a transconductor, okay. So this gives, if I call this GM1, this is IGM1, and this, I connect the capacitor across this, let me call it C1, okay. So now essentially this IGM1 is converted to a voltage VC1, which is the integral. Now what is the problem? We have the parasitic element RO1. Now whatever the voltage across the capacitor is, that is also appearing across RO1. That is the problem. Okay. So we can think of this as a problem of making a better current controlled voltage source. GM is providing the current, okay, and if you pass that through some impedance, you will get a proportional voltage, okay. You will get that current times the impedance as the voltage. Now the point is that same voltage also appears across the output conductance of GM1 itself, okay. So this business of, if you have, this is a standard problem, right? That is, you have a current and you have to convert it to some voltage by multiplying it with an impedance. Ideally, you will get I1 times Z. But if the current source has some internal resistance, okay, what will you get? You will get I1 times Z parallel RO1, okay. So this way of converting I1 to a voltage by connecting the impedance directly across the current source, this is not the best way to do it, because then the same voltage appears across RO1 and it will steal some of the current, okay. So now the question is, can we have a better current controlled voltage source? This is the idea with the current controlled voltage source, right? What is the difference between just connecting the impedance across a current source and a current controlled voltage source? What is the property of a current controlled voltage source? So, or any of these control sources, right? What is the feature of all of these? Now, any amplifier that you take or any circuit that you take, if it has two terminals, obviously it will have some input current and input voltage. You can always refer to the any quantity that you want, either the voltage or current as input, and call it a control source. Can you do that? That is, I give you a block and I mark V1, V2 here, and then say, oh, there is voltage input, voltage output, so it's a voltage controlled voltage source. And you instead mark the current and a voltage here and say, oh, no, this is a current input, voltage output, so this is a current controlled voltage source. Is this what a current controlled voltage source is? What's the difference? What is it? Yeah, so it's characterized by whether it's which kind of control source it is, it's characterized by the input and output resistance. The idea is, if it is voltage controlled, then it should not be sensitive to the series resistance of the input voltage source. Okay. then whatever even if you have an imperfect voltage source, it should sense the voltage without being affected by the resistance, and it will do it only if the input resistance is very high or infinity. Similarly, if it's a current controlled voltage source, it should not be sensitive to the internal resistance of the driving current source. Okay, so that's what distinguishes. Otherwise, you can label any variables, and that you can still do, right? For any circuit, instead of describing what V out by Vi is, you can give what I out by Vi is or something, but that doesn't make it a control source. Okay. Similarly, on the load side, it's a voltage source if the voltage is independent of RL, and it's a current source if the current is independent of RL. Okay. So now I think this is also something you are familiar with. So instead of just sticking an impedance across a current source to get the voltage, we have to make a current control voltage source whose output voltage is, let's say, I1 times Z. Okay. This is what we want to do. So how do we do this? What is a good way of making a current control voltage source? Huh? What will that do? But that's not a V. This is here we want a current control voltage source. What is a good way of getting any relationship? Yeah, I mean, by now you should know. I know only a couple of things. Negative feedback is one of them. So answers to half the questions can be negative feedback. Okay. So we can use negative feedback to realize this current control voltage source. How do we do that? How do we, I mean, let's say you have a relationship and you want to realize it using negative feedback. What is the essential part? What is negative feedback? You have to have some comparison. You have to have some measure of error, and you should drive the output based on that error. Okay, you should continuously adjust the output based on some error. So in the direction that the error goes to 0. Okay. So now here, what is an error that we can define? I mean, basically you have to rearrange the relationship that you want so that if it goes to 0, you get the right relationship, right? I mean, this involves some trial and error. This is how you would do it in design. So here, one possibility, let's say, is V0 minus I1Z equals 0. Okay. So what does it mean? I have an input current I1, and somewhere in the circuit, I have to produce an output voltage V0. So let me mark those things. So I have V0 here, and of course, this Z must be available because it's a dimension quantity. So I have to have Z available in some form in the circuit. And I have the current I1 somewhere, and I have an impedance Z somewhere. Okay. So first of all, how do I get this V0 minus I1Z? What should I do? So first of all, I1Z, that means this current I1 must be flowing through Z, right? Okay. And then, so then we'll have I1Z there. Okay. Of course, here I know the answers. I'm going quickly through it, but if you're designing circuits, this is what you do. You try to rearrange the relationships that you want into various forms, and then basically force the circuit to give you the result that you want. Okay. So V0 minus I1Z, what should I do? No, I just want to first get V0 minus I1Z. Where will I get that? If I just connect it here, this is at V0. So this node is at V0 minus I1Z. Okay. Now, based on this, I should control the output. So what should happen if V0 minus I1Z is less than 0? What should happen to V0? I can only hear crease. V0 must decrease. Okay. V0 minus I1Z is less than 0. It must increase, right? V naught must increase. Okay, and of course vice versa. So how do we do that? What do we use to drive the output? Now let's not get into transistor level details. What was the central element of the negative feedback? Integrator. Okay, so you use an integrator to drive the output, but here if this voltage is negative, the output must go on increasing. So it must have a negative polarity. Okay, something like this. Okay. Now what is the integrator? Basically that is the opamp, right? Yeah, we'll get there. I will show the opamp like this. Okay, something like that. Okay. So this is some other, I mean, let's say this is some GM2 and C2. This is your opamp, or rather, maybe let me draw something else first. Let me show the this is the opamp. Now, of course, if you already have an opamp, like you pointed out, why do you need to build an opamp using that? So what do? You essentially use the opamp that you have. That's the only opamp that we know so far, right? That single stage opamp. So we can stick it in that place and then see what happens. Is this logic clear? So that I to V conversion itself is realized using negative feedback, and for that negative feedback you need an opamp, and you use the only opamp that you know so far, which is the single stage opamp. Is this okay? Any questions? So first of all, this circuit itself, is it familiar? This one? What is it? It's basically the standard current controlled voltage source or the transimpedance amplifier. Okay, so instead of connecting the impedance Z across the current source, you make a transimpedance amplifier so that you have a better current to voltage conversion. Now, of course, you won't have the op-amp to put here, so you have to use whatever op-amp you have, which is the single stage op-amp. Okay, so now what were we trying to do? This current is basically the output current of this GM, right? And what is the Z? Z is the capacitor C1. So let's do that. So essentially what we need to do is have GM1 through this capacitance C1. Okay. So now you also see that this current source is pointing downwards. So it should be like that. Okay. So that GM1 we flows in that direction. Now before I go further, what is the transfer function of this op-amp, assuming an ideal op-amp here? Of course, it doesn't make sense to have ideal op-amp here. I understand that. But what's the transfer function of this op-amp? What will be V naught? What is it? Huh? GM1 VE? Yeah, it will be basically VE times GM1 by SC1. That's the point I wanted to make. The transfer function is exactly the same as before, assuming ideal components, right? So earlier also we were trying to get an integrator whose transfer function was GM1 by SC1. Now you will get exactly the same if you have an ideal op-amp. Of course, we don't have the ideal op-amp. We substitute it with the op-amp that we have. Okay. What is that? So basically you will have to do this. You have GM1 and you have C1 across this, and ideally you are trying to get GM1 by SC1 times VE. Okay. And what you have here? I'll just put some capacitance. Again, it may be deliberately placed, or it could be the load, or it could be the parasitic of the stage. Okay. So this is my internal opamp. Okay. So now what is this circuit? Is this familiar to you? It's a two-stage Miller compensated op-amp. But what I wanted to make emphasize here is you're still trying to make an integrator whose unity gain frequency is GM1 by C1. Okay, and this is some auxiliary help. This is something important to realize also. That is, of course, many times you would analyze this circuit in isolation, and then you find the DC gain of this whole thing, and then find the pole, and then multiply to get this GM1 by SC1. But you should realize that the second stage with this C1 in feedback is acting like an integrator. Okay, so that's why you get GM1 by SC1. This part, this result you know, right? Two-stage Miller again is familiar to you. So what is the unity gain frequency of the two-stage Miller compensated op-amp? It is GM1 by SC1. So that you may have derived by taking the product of the DC gains and the pole value and multiplying and so on. But here you have to realize that actually you are trying to realize an integrator. Okay. So that's why you still get GM1 by SC1. Of course, because of the details of the second stage is not perfect. These numbers can be modified a little bit. But the essence of the circuit is still an integrator whose unity gain frequency is GM1 by C1. By the way, what happened to the output resistance of GM1 now? Let's look at it with the ideal op-amp. The point is that this RO1 now is across the virtual short. It won't draw any current. So you don't have that earlier problem anymore. Because earlier, if you had any output voltage, there would be that voltage across RO1 which was drawing current, which had to be supplied by GM1. Now the voltage across this is 0. So with DC steady state, the GM doesn't have to supply any current. So that means its input voltage can be 0. Now in reality, what happens? This voltage will be non-zero, but it will be smaller than the output. That smaller voltage appears across RO1. So now the input voltage is non-zero, but smaller than what it was before. Okay, so we have got some improvement. We'll of course do the quantitative analysis. I think you're already with analog systems and analog circuits, you have know enough analysis to sit and analyze this to death, but you should also have an intuitive picture of where this comes about. Okay, is this fine? So essentially, you try to use negative feedback to improve this current to voltage conversion and result in a better op-amp. So now that internal negative feedback loop requires another op-amp, and you use whatever op-amp that you knew, that single stage op-amp, to put there. Okay, is this clear? Right. Exactly. So the gain of the second stage helps you, right? So the second stage also has a gain. So that's another way to think about it. This output voltage doesn't appear across RO1. Some fraction of that appears across RO1. So the current that you have to drive from GM1 is much smaller. So that means the input error voltage is much smaller. So which basically makes the virtual short better. Okay. This is okay. Now, of course, you have to put in all the details and then analyze this, because now you have a more complicated circuit. And one thing I have not shown here is there will also be a parasitic capacitance here. Okay. And so on, right? So these things have to be changed. Maybe it is better I call this C and I could call this C1. Anyway, whatever it is, there will be some parasitic capacitance here. You have to analyze it. But then that part you already know, the circuit analysis, and we will again go through it. But it's important to understand how we got the topology. Okay. So now let's say the first stage has an output resistance RO1. The second stage has an output resistance RO2. What is the DC gain of the entire op-amp now? So by the way, this is the positive terminal of the op-amp. This is the negative terminal, right? Because this GM had to be inverted. to get the current direction correct. So what is the DC gain of the op amp? I mean, how do you evaluate DC gain of any circuit? You open circuit all the capacitors and do it. So what's the DC gain? GM1 R01, GM2 R02. Basically, it's the product of two DC gains, right? So if you're the single stage, you are getting gains of a few tenths. With two stages, you will get a gain of few hundreds. Okay, so that's the improvement that you've got. This is of the order of product of two intrinsic transistor gains. Okay. There are many combinations that are possible. I will go into that after we come to the transistor level. But the essence of the circuit is to make better I to V conversion. Okay. You're still trying to realize an integrator with a unity gain frequency GM1 by C1. Okay. Any questions here? Now also earlier when you had only a single stage, I said I'll have a buffer here so that it doesn't disturb the DC gain. That is, if you don't have a buffer, what happens is this resistance K times R appears across the output resistance and your DC gain is severely compromised. Okay. Now with two stages, also you can use a buffer, but buffers are also not easy to realize. Now the important thing is that if you have a resistive loading here, the gain of the second stage will be reduced, but the gain of the first one will not be affected, right? So you could probably live with a small gain in the second stage and try to get high gain in the first stage. So this, especially we'll see actually when we come to buffer circuits, you know that, I think you probably already know this. What is the buffer? What circuit can you use as a buffer, voltage buffer? Common drain or a source follower, right? But the source follower has very poor swing limit. Okay. So you can't, what is the best swing that you can get? Let's say you have transistor circuits and you have VDD and 0. What is the maximum swing that you can get? Generally, I mean, without using inductors and things like that. So basically within, why VT? But why is threshold voltage relevant? The output voltage that you can get from any circuit which is operating between 0 and VDD, what is it? Ideally, of course, it's VDD, but you have to implement this with transistors. So what is it that you typically get? What is the minimum that, see, you have to drive the output, okay? So that means that actually there has to be some path to the upper rail, some path, there has to be some this thing, and then some paths to the lower rail. And whatever circuit will demand some voltage across it. Otherwise, you can't have operating, you can't have zero operating point, right? No, sir, no device will work like that. So what is the minimum that you need to have on the upper side and the lower side? So basically, the best case would be you have just one PMOS transistor on the upper side. I'm not showing any specific circuit here, but just to be able to drive that, you need to have that and one NMOS transistor on the lower side. So you need to maintain, I hope you are familiar with this notation. This is VD sat of N at whatever current it is operating, right? And similarly, this is VD sat P. So if you, within your supply rail, you lose VD sat P over there and VD sat N over there. So the maximum to minimum, the peak to peak that you can get is VDD minus VD sat N minus VD sat P. Okay. So this is the maximum, let's say if you had a sinusoid, this would be the peak to peak of the sinusoid that you can accommodate. Okay. Now, of course, many circuits are much worse than this. The source follower is one of them. Its swing limit cannot be this high. Okay. And of course, with the reducing supply voltage, it has become quite important to have the maximum swing that is possible, right? So that's why this type of stages are preferred. Okay, but in this case, when you have two stages, it's okay. The second stage gain becomes worse, but at least you have the first stage gain which is not affected. So you may still be able to work with if you have a resistive load. And it's frequently used like that. Okay. In fact, in the next assignment, you see an opamp which model and so on, which does the same. Okay. So now we'll continue from here. But let's say I'm still not satisfied. This GM1 RO1, GM2 RO2 doesn't do it for me. So what should I do next? What is I want to improve it further. What could I do? So basically, see, this would work perfectly, right? If it had an ideal op-amp, you would get this. Of course, if you had an ideal op-amp, you would use that instead. So now you've already made a better op-amp, you plug that in there. Okay. So you take this whole thing and use it in place of that. Okay. So you can keep going. So this is what I want to build. Okay. And inside, I'll now I already have this part. I'll do that. So this is my inner op-amp. Okay, and that op-amp itself is built with another inner one. And I can have more stages also. Roughly speaking, what's the DC gain of this? It's basically a product of 3 stage gains. So you can get, I've seen up to 5 stages also. Normally you don't do it, but you do it only if necessary. But it is possible. But the point is not to think of all these things as like different circuits or something, right? You're improving the I to E conversion, and as and when you make better op-amps, you could probably use them in place of that ideal op-amp. Okay, so we'll continue from there, and all this, of course, all this extra circuitry brings in more parasitics, more details, which our analysis skills will take care of. Okay, any questions? So you can also quickly see how the number of topologies can blow up. And if you don't have some logical links between them, it's very easy to get confused.